Have you ever wondered why planets in the solar system revolve around the Sun in stable orbits for billions of years? What governs such movements between faraway objects? Inspired by the fall of an apple from a tree, Sir Isaac Newton hypothesized the theory of gravitational force, which is described by this beautiful and concise equation on the left. In this equation, m1 and m2 are the masses of the objects, r is the distance between these objects, and g is the so-called gravitational constant. But how can we even determine the value of the gravitational constant? The original experiment to determine the gravitational constant conducted by Henry Cavendish is nothing short of remarkable for its time, as the accuracy of Cavendish's results would not be surpassed for over a century. And though much has changed since the 18th century, the basic principle remains the same, measuring the gravitational constant force of attraction between small objects. Here are all the variables needed to determine the value of g in the Cavendish experiment, followed by the equation below. Delta S and T are the changing variables and will be collected during the experiment. The tungsten balls were rotated from a primary position to a secondary position for an hour, and were then rotated back for another hour, which resulted in an oscillation of the laser spot. From these oscillations, two separate equilibrium points were determined using the tracker software, with the difference between these 2 points equaling around 0.15 meters.
Each rotation of the torsion pendulum and the oscillation of the laser spot resulted in two unique damped sine functions. These functions rotated around separate equilibrium points, with a difference of approximately 0.15 meters. The first oscillation period is represented as the green sine function, and the second oscillation period is represented as the red sine function.
This table summarizes all of the values found in this experiment, including the gravitational constant, g. The value of g was found using the equation below. The error in g was also found. It was determined that the largest contributor of error was b, which is the distance between the center of masses for the large and small ball. Our calculated value for the gravitational constant was very close to the accepted value, being within a 2% margin of error. However, our calculated value was not as accurate as the value determined by Cavendish, which was in 1% of the accepted value.
We sought to conduct a modern variation of the Cavendish experiment for finding the value of the gravitational constant. Our final result for the gravitational constant was determined to be 6.6 times 10 to the negative 11.